Welcome back. Part 2, Part B, buoyancy and stability. So we'll talk about stability now. We know that the buoyant force is just equal to the weight of a fluid that is displaced by a submerged body or just a submerged part of a floating body. Now we want to talk about, we have a body, it's submerged or partially submerged. How do we know it's stable? Which means, how do we know it's going to stay upright? When we look at some objects that are floating, it can be kind of difficult to figure out what actually makes an object stable. So what is the actual forces acting on this sailboat, for example, that is counteracting the forces of the wind acting on the sails, causing it to tilt? So this boat is tilting quite a bit. So what is this righting force? We'd have to apply a moment this way for this to be stable, and that moment must be due to stability of this vessel in the water. So what's causing that? Here's another question. Is this ship stable? What do we think? Yes or no? Yeah, this is even though it doesn't look in the stable position that you would want a ship to be in, it is actually stable. So it's still floating in this picture. I mean, difficult to tell, but it was no longer stable in its upright position, and it became stable in this. Maybe it's because it took on water or got pushed too far beyond its stability point and moved to a new stable position. So a floating object may have more than one stable position. So how can we calculate whether or not an object is stable? So let's assume we have the object, an egg-shaped object in figure A. So if the floating object is disturbed with some small angle, delta theta, then we can have the following two cases. So if a floating object is disturbed with a small angle delta theta, then we could have two possible cases. So this is our floating object right here. It's disturbed some small angle delta theta. There's two cases we could have. We could have one where there's a restoring moment which is generated, which means that the center of buoyancy moves in such a way that the moment that's created between the weight and the buoyant force wants to bring it back to that position before it was disturbed. Or we could have an overturning moment. So in that case, maybe the center of buoyancy does not move enough, and the moment that's created from the weight of the object and the center of buoyancy makes it so it's unstable, and it wants to increase that angle delta theta. So we could have a system over here, figure B would be stable. My writing is so messy on this thing. Stable. And over here, we would have a condition where we would have an object that is unstable. And these points right here, B, this is our center of buoyancy. And where G is on all these figures, this is our center of gravity. So how do we determine where this new center of buoyancy is, or the new center of gravity is? How are we going to assess this stability? So let's look at a ship profile, for example. If we were to view it from the top, what we would see is the footprint. And we would really only care about the footprint at the waterline. So when we talk about the footprint at the waterline, this is what we're referring to. So if we have our ship, we want to test if it's stable. Let's artificially tilt it some small angle. And then we also have to assume that in order to do this calculation, the body has a smooth shape. There's no discontinuities in the shape near the waterline. And we also have to assume that it's symmetric about that vertical y-axis. So we don't have an asymmetric shape, and we don't have a shape with maybe jagged edges or parts missing. Assuming it's a nice regular shape, and it is symmetric about that vertical axis. All those things have to be true for this analysis to work. Otherwise, you'll have to get into more difficult computational methods to determine stability. But for general shapes, we can use this method quite easily. So here is our cross-sectional view of our ship, and we'll go into that a bit more detail. So a few things we need to do to assess stability of a floating object. So the first one, we need to compute or figure out where the body's center of mass, G, is, and the center of buoyancy for the upright position. So we need to find or calculate center of mass or center of gravity, and that's at point G. And center of buoyancy, in this diagram that is capital B, in the upright position. So that's our first step. Once we have that, what we're going to do is we're going to tilt the body some small angle theta, and we find our new water line. We're going to calculate the new position of the center of buoyancy. So the center of mass, the center of gravity of the object isn't going to change. It's just the center of buoyancy that's going to change. And because this is a floating object, we care about the center of mass of the entire body. So only the center of buoyancy is going to change. So for step 2, we're going to tilt a small angle theta and find new water line. And then we're going to calculate the new position of the center of buoyancy. And we'll call that B prime. And this, if we draw a vertical line up from this point, this will intersect with the line of symmetry at a point called the metacenter, or point M. So we look over here, we had our original center of buoyancy, and we have our new center of buoyancy after we've tilted it some angle. And if we draw a line vertically upwards from that new center of buoyancy, where that crosses the center line of our symmetric object is called our metacenter. And B prime here is our new center of buoyancy. So let's write this. We tilted the body a small angle, we found a new water line, we calculated the new position of the center of buoyancy, which we'll get to, and that's a distance x bar away from that line of symmetry. And then if we draw a line directly upwards from that new buoyant line, that will cross the line of symmetry at a point called the metacenter. So the next thing would be draw a vertical line upwards from B prime intersecting the line of symmetry at M, which is the metacenter. Line of symmetry. Okay, so those are the first two steps. So now we can determine, if we know where the metacenter is, we can determine whether an object is stable or not. Let's just relabel some stuff here. We have our metacenter, new center of buoyancy. This is our vertical line. So if our metacenter or point M is above center of mass or center of gravity G, a restoring moment appears and the original position is stable. Whoops. So if M is above G, a restoring moment appears and the position is stable. So likewise, in the opposite case is true. If M is below G, then the body is unstable and it will create a moment that will cause the body to be overturned if it's disturbed at all. So if M is below G, what will cause an overturning moment appears and body is unstable. So that's basically our steps. We have our shape. We're going to calculate the center of mass and the center of buoyancy. We're going to tilt it slightly for some small change in the tilt of the vessel, and then we're going to calculate the new center of buoyancy. And if the vertical line upwards from that new center of buoyancy is above our center of mass, then the moment that's generated from the buoyant force and the mass acting through the center of mass creates a righting moment, and our body is stable. Otherwise, our body is not stable, and it will just continue to tilt until it reaches a stable position. So how do we actually calculate this new center of buoyancy? So the center of buoyancy is going to be acting at some distance x bar away from our symmetric axis, and that's going to be in the direction of the original horizontal position of the boat or the object. So we can think of calculating this x bar as the if we wanted to have a resultant force, just like we did for forces on curved surfaces, the resultant buoyant force of all of the submerged sections of the body compared to the original submerged body. So let's just write some equations and then we can sort of discuss what they mean. So we can start off by writing that x bar times the volume of the submerged section, which is section AOBDE, A, lowercase a, so AOBDE would be here, so A to O, B, D, E. So the moment created by, or the equivalent center of this volume would be equal to the center of the volume of the body CODEA. CODEA was the original. Plus this new submerged section. So that's going to be OBD. Let's draw this in blue. So this is section OBD. And then minus the section that's no longer in the water. And see if yellow works for this. So that's this section over here, which is now above the water. So this would be section COA. So we're going to subtract COA. And what this is doing is finding the average center of these bodies, because our fluid that's providing the buoyant force is a uniform fluid. So we're basically finding the new center of this object. So if we solve for this, we'll find that the original shape, because it's symmetric, the distance to the center, the x distance to the center of the original shape is 0. So the first term is 0. And then our next shape, we only have the two integrals OBD minus COA. And if we have a regular shape, and we're only caring about our profile or cross section right here, then we can simplify this further, and we can replace our dVs with L times the area dA. Ooh, that's too big. So we can rewrite this now as L times dA and L times dA. So if we can simplify it a bit further, if we even have a more simplified object, we still have 0 for that first term, so let's just get rid of it. We can simplify the first integral xl, and then that area integral, if we just integrate over x, we would take x tan of the angle of tilt theta times dx. So this is OBD, so we're just integrating over the area. So as we move further out in the x direction, the other dimension we care about would be tan theta times x times dx. So that's our dA right here. So we can do this for both sides, or both of those terms. And we get COA XL x tan theta dx. Is that we have our tan theta can come out of these terms, and it simplifies to the integral of the water line, the footprint of the water line, times x squared dA of the water line. And what we really care about now is just this final equation, I0 times tan theta. So we should recognize that the integral of a dimension squared over the area of some volume is equal to the moment of inertia. And in this case, I0 is the moment of inertia of the waterline footprint. Inertia of waterline footprint. So we have our equation x bar times the volume of the submerged region is equal to I0 times tan theta. And if we go back up, we showed earlier what the volume or the footprint at the waterline. So we would care about this I0 of this shape. And we're calculating a moment of inertia. And if we think about that, if we have an object that has a larger moment of inertia, that means for some tilt, a larger moment of inertia would create a larger displacement of our center of pressure. And if we have a larger displacement of our center of pressure, there's a higher likelihood that that metacenter will be above our center of mass. So for stability, having a larger I0 or a larger footprint tends to be related to having a more stable object. So next we can write we'll just rewrite our equation up here. X times V of A0 BDE and this here, it would just be the volume submerged. Whoops, it's not equals, it's times. So we can say the line from M to B is equal to X bar over tan theta. I'll draw this bar a little smaller. X bar over tan theta, just by geometry. And this is equal to, if we use the equation above, X bar over tan theta is equal to our I0 divided by the volume submerged. And this is also equal to, if we just add up those lengths, it's equal to the length of line segment M to G plus G to B. So what is this here? M to B is this length here. So all we care about is this distance from our meta center mg to our center of gravity. So if we rearrange this equation, mg is equal to the distance from our meta center to our original center of buoyancy minus the distance from center of gravity to our center of buoyancy. And we know mb is equal to I0 over the submerged section, so we can write this again as just I0 divided by volume submerged minus the distance GB. So I'll just define a few things here. mg is the distance from center of gravity to meta center. mb is distance from center of buoyancy to the meta center. And then GB is the distance from our center of gravity to our center of buoyancy. So what did we say before? We said that if our metacenter was above our center of gravity, then we had a body that was stable. And if we said it was below the center of gravity, then we said our body was unstable. So by this equation, this would mean that if mg is positive, we have a stable system. But if mg is negative, we have an unstable system. And the body is unstable. Okay, so let's just recap. So what we did, we had our system, we had our shape, we calculated the center of mass, we knew where that was, and we calculated the center of buoyancy, and that would be some distance away from the center of mass. It'd be the center of area of the submerged section. We applied a small tilt, and we found B prime. And how we did that is by finding the equivalent area, essentially. We wanted to find the new center of buoyancy, the new center of this area. So we would have to take the x dimension multiplied by each differential volume and integrate over the entire volume of the submerged section. And the volume of the submerged section is the volume of the original section, plus the volume of the new section over here that is in blue, that is newly underwater, minus the section of the volume that is now above the water. And we simplified this and we ended up with getting our moment of inertia of the waterline footprint times that angle tan theta that we have disturbed our shape. And then just using geometry, we calculated the distance from our metacenter to our center of buoyancy is equal to the moment of inertia divided by the volume of that submerged shape. So that's our equation right here. And then we also said the metacenter, or the distance from the metacenter to the center of buoyancy in this next equation here is also equal to the distances mg plus gb, which are these two line segments here, mg and gb. And we have an equation above for mb. So mb, and we substitute that in and we rearrange, we get an equation for the distance from the center of gravity to the metacenter. And if that distance is positive, we are stable. And if it's negative, then we have an unstable system. Okay, if it is symmetric, why do we need to do the addition and subtraction of the two pieces? Wouldn't the volume be the same without that part due to symmetry? Not necessarily. What if our shape looks like this? Where would that go through? So now our new submerged section would be here from our original section, but our unsubmerged section is now this. So those aren't quite the exact same. We can see that the areas right here are different. So in this case that we drew, because we had just vertical sides of our hull, yeah, it would appear that way. But if we don't have vertical sides to our hull, then that's not necessarily the case. So we can see that the red shape that we just drew, if we don't have vertical sides to our hull, we have a V shape. When we actually tilt it, we have more of the body submerged than we have actually come out of the water. So our center of the submerged volume is going to move more from that center line than if we just had our vertical hull sides. So that's why you see a lot of ship design has that V shape. It's a more stable shape in the water. All right, let's do a couple examples. So the first example, we have a barge. It's 15 feet wide, 40 feet long, and it floats with a draft of 4 feet. So a draft refers to the amount of, or the depth of the vessel below the surface of the water. So if you have a boat that has a draft of 5 feet, that means if you were in water that was only 4.5 feet deep, you'd be hitting the bottom because your boat is 5 feet deep. So it says it's piled so high with gravel that its center of gravity is 3 feet above the water line. Is this stable? So let's first draw a diagram of what this looks like. So we have a barge. Let's look at the cross section somewhere in the middle. So let's do a cross section here. So it doesn't tell us much information about our shape. Let's assume that it's just rectangular. We have our water line. We have our line of symmetry. Our center of buoyancy is going to be the center of the shape that is submerged. So B is going to be down here. And it tells us that it's piled so high with stuff. Here's all the things in it, that our center of gravity is actually 3 meters above, or 3 feet rather. And it also tells us our draft is 4 feet. And then the last thing we care about, it's 15 feet wide. So if it's symmetric, that means that there has to be half of that distance, 7.5 feet on each side. So we can write 7.5 feet. Label this as our water line. And then the last dimension it shows us is 40 feet long. So let's draw this on here maybe. So there's our diagram. So is this stable? What else can we learn from this so far? We know the distance from the water line to our center of gravity. What is the distance from the water line to our center of buoyancy? So Hector, to answer your question, says the length doesn't really matter because in our equation, if we go back, we need to find this I0, and that's I0 for the footprint of the vessel at the waterline. So we will need to actually calculate using that length. We need to use that length to get our I0. But yes, Ahab and Jaden's correct. Our center of buoyancy will be 2 feet from our surface because that's the center of the submerged section. 2 feet. So let's write our equations. GB in this case can be equal to 3 feet plus 2 feet and then our distance from the metacenter to our center of gravity is equal to I0 over the volume submerged minus GB. So what is I0? So in this case, I0 is the moment of inertia about the tilt axis of the footprint. So if we were to draw our footprint, this is 15 feet, and this is 40 feet. This is our tilt axis line of symmetry. So we would have our I0 is equal to 40 feet times 15 feet squared or cubed divided by 12. That is the moment of inertia of a rectangle. So if we want to remember which dimension is cubed and which dimension isn't cubed, the dimension that reaches away from our center of tilt or center of rotation or a pivot point is going to contribute more to our moment of inertia. So if our boat is wider, that should contribute to our stability or moment of inertia much greater than if our boat is longer, because it's going to tilt about this length axis. So the 15-foot dimension is one that is going to be cubed because that's going to contribute to having more of the boat further away from that tilt axis. So it's 40 times 15 cubed divided by 12, which is equal to 11,250 feet to the power of 4. The volume submerged is just equal to the draft times the length times the width of the boat. So that would be 4 times 15 times 40, which would be equal to 2,400 feet cubed. So we can rewrite mg is equal to 11,250 over 2,400 minus GB, which is 5 feet. And this would be feet to the power of 4 or feet cubed. And our final answer would be negative 0.312 feet. So mg is less than 0. So this barge is piled too high. It's unstable. Let's do another example. So this time we have a wooden cylinder, gives us our specific gravity is 0.6. It is 1 meter in diameter and 0.8 meters long. Will this cylinder be stable if placed to flow with its axis vertical in oil? And oil's specific gravity is 0.85. So let's start with the same place as before. Let's draw some diagram with some dimensions that we care about. So we're assuming this is a uniform block. So the center of gravity will be acting in the center of the block. And the center of the block would be halfway from the top to the bottom. So it's a 0.8 meters long. So that would be 0.4 meters from the top surface. And we need to find the center of buoyancy. The center of buoyancy will be the center of the section that is submerged. So if we had the total submerged section is H, then the distance to our center of buoyancy would be H over 2. So where would we start? What are the steps we need to take to solve this one? Right, we'd have to find H first. We have to find that depth. Once we know the depth, we can calculate our distance to the metacenter. And we know our I0 of the footprint because it's a circle, so we can solve for stability. So yeah, just to go back to the question in the chat, in the previous example, because that distance, the metacenter to the center of gravity was negative, we calculated mg as negative. That means that for any small tilt, the buoyant force and the weight of the object would create a moment that would cause it to continue to tilt. So it would be unstable, it would continue rotating. So it would be in that unstable position, essentially it'd be balancing. So if you were to hold a pencil upright on the end of your finger, there is a balancing point where it is stable. But the second it tilts slightly off your finger, it's unstable and it will fall over. This is the same kind of principle here. So let's first, for this problem, find the depth of the submerged part. So in order to find the depth of the submerged part, we need to find the equilibrium or solve for equilibrium of the buoyancy. So from equilibrium, we know the buoyant force must be equal to the weight of the object. So the buoyant force is the specific weight of the fluid, which is oil, times the volume displaced. And that is equal to the specific weight of the wood times the volume of the cylinder. So the specific weights, we can use specific gravity times the specific weight of water. So we'll have that specific weight of water term on each side of the equation. So we can just rewrite this as specific gravity of oil times the volume that's submerged would be a distance h times the area, pi over 4 times the diameter squared, which is equal to the specific gravity of wood times the volume of the cylinder, so that's 0.8, or we'll call it L, times pi over 4 d squared. So notice we have the same area on both sides, so these can cancel. So it doesn't matter the diameter. And what we're left with is h is equal to the length times the specific gravity of wood divided by the specific gravity of oil, which is equal to 0.8 times 0.6 over 0.85. Final answer, 0.565 meters is h. So we know h. We solved for that equilibrium for buoyancy, so we know how deep this object is floating in the water if it maintains this position. Now we have to find the distance of the center of buoyancy to the center of gravity. So we said, let's draw it again here. This is B, and it's equal to h over 2. And our center of gravity is equal to L over 2 from the top. And lastly, we need to know what the moment of inertia is. So if we remember back to the moment of inertia, our footprint of the waterline will be a circle. And the area, pi r squared, I0 would just be pi r to the power of 4 over 4. So let's write in some of these values. We knew h over 2 is equal to 0.565 over 2, which is equal to the distance from G to B is 0.4 meters. That's L over 2 minus 0.282. So we could draw this side as h over 2 as well. So this might be easier for calculating GB. So the distance GB is equal to 0.118. So then lastly, the distance from our metacenter M to our center of gravity G is equal to I0 divided by the volume submerged minus GB. So this is equal to pi over 4 r to the power of 4 divided by our submerged volume, which would just be h times pi r squared. minus GB, which is 0.118 meters. So we did this, our pi's cancel out. This just becomes a squared. We get r squared over 4h minus 0.118, which is equal to negative 0.007. So again, this shape is unstable in this orientation. If you think about it, maybe something that could be that shape, an empty water bottle perhaps, or a cork. I've never seen a cork or a water bottle float upright like this. It's always floating on its side because that's the actual stable position. So what if mg is 0? So if mg is 0, we have like a quasi-stable state. So a slight disturbance will not generate any righting moment or overturning moment. It just won't generate a moment at all. So if we think about if we had a sphere in the water, it doesn't matter which orientation that sphere is, it's always stable. If you tilt it a little bit, it's just going to stay in that new tilt position. So it just means you have a state where if you have a small tilt, the position of that small tilt is also stable. So we'll call that, like, if mg is equal to 0, that is a quasi-stable state. All right, let's do one more example to finish off today's lecture. So in this last one, we have the sketch shows a flat bottom blunt nose river barge, which is nice, rectangular, used to carry bulk materials. Assume the barge's center of gravity is at its centroid and that it floats with 8 feet submerged. Determine the minimum width of the barge that will ensure stability in seawater. So what is that minimum width? How wide does this barge have to be so that you can stack it and bring up its center of gravity to point G, which is 12 feet up from the base, and it has a draft of 8 feet. So if we have our diagram here, where is the center of buoyancy? Right. It is in the center of the area of the submerged volume. So the submerged volume is rectangular. It's 8 feet deep, so it's going to be halfway down. So it's going to be at 4 feet deep. So if this is our case, we know that GB right off the bat, we can calculate as this distance here. And if we relate this to the distance from the bottom of the boat, from the bottom of the boat to the center of gravity is 12 feet. And then if we subtract from the bottom of the boat to the center of buoyancy, that's 4 feet. So we should get our distance from our center of gravity to our center of buoyancy is 8 feet. So our center of buoyancy is 8 feet below our center of gravity. So now let's calculate mg. It's I0 divided by the volume submerged minus GB. What is I0? What is I0 for this? It's going to be some dimension times some dimension cubed divided by 12 because we have a rectangular barge. Yeah, so it'll be that length, 80 feet, times our width, W, to the power of 3 divided by 12. So 1/12 length times W cubed. And our submerged volume would be equal to W times L times H, right? Width times length times the draft. So let's put this all together. Mg is equal to 1/12 LW cubed divided by W times L times H minus 8. So we're solving for the minimum width W so that we have a stable system. So essentially we're solving for when this quantity is going to evaluate to a number larger than 0. So we care about when this is greater than 0. Or basically, if we simplify and get rid of the cubed, we care about the condition where 1/12 the lengths go away too. So 1/12 W squared is equal to or rather, I should be more complete, is greater than H times 8. Or we can say W must be greater than square root of 12 times 8. We said H was our depth, and that depth is 8 feet. So W must be greater than 27.71 feet. So for this barge to be stable, it has to be at least, say, 28 feet wide. Are there any questions about stability as pertains to fluids? Well, if there's no questions about this so far, maybe we'll let this sink in. Oh, one question. We talked about how a sphere is quasi-stable earlier. Is there any practical application of a quasi-stable object? I imagine there would be. I don't know. Most of my background has been with solid mechanics, not too much the interaction with fluid and stability. But if you wanted to have maybe an object that didn't care whether it was upright or not, and it was traveling over the water or through water, maybe you would want to design something. Or maybe there's some interesting properties of shapes that have quasi-stability at different orientations. Basically, what that quasi-stable point, if mg is equal to 0, it just means that the metacenter is at the center of gravity. So if we tilt the body at all, that means the center of buoyancy remains directly below our center of gravity. So that line that we draw vertically upwards from our new center of buoyancy stays directly below. So the only shape I could think of offhand right now that fits that description would be a sphere. How much of the derivation do you need to remember? I'm not going to expect you to be able to derive the center of buoyancy as we've done before. I'm assuming that if we've derived something in class, then you can always assume that that derivation is true, and you can use that equation at the end that we've come up with. So all I really care about is understanding how to implement the equations for, where are we here? The equations for stability and the equations for buoyancy, essentially. So this is, if we're starting from this point here, then that's fine. An extension could be if we really wanted to use this top equation up here. So this equation, we could say for a specific shape that's floating, if it is tilted this much, what is the displacement, or how much does the center of buoyancy move? And that would be solving for x bar. But for most cases, we just want to evaluate whether something is stable or not. We're not necessarily trying to find its stable position. So if that's good for questions, the second quote of today, for the second half of the lecture, is a quote by Leonard Euler, famous mathematician, probably one of the fathers of mathematics. For the sake of brevity, we will always represent this number 2.71828128459 by the letter E.